consequences for me. At the end of class, at the end of the lecture last time, Sam pointed out that I said something wrong. I don't know if it, so this is just a quick comment. Last time we were taught we had the right-angled Martin group, and we also had the idea of right-angled Coxeter group. And I wanted to say that any right-angled Martin group was commensurable with a right-angled Coxeter group. And in particular, you could use that to show that these were residually finite. But to do that, I had to form two other graphs. One is more important than the other. That was what I call O of gamma. This was sort of the doubled graph. Okay. So every time you saw a vertex, you took two copies of it, and every time you saw an edge, you took four copies of it. And if you didn't have an edge, you didn't do anything. And the other hand, I had something which I call delta of gamma, and I gave the wrong definition of this. So the right definition was you double the vertices. So you double the vertices. You take the vertex set of the original graph cross 0, 1 or something like that, and then you connect vertices of the form, say I1 is connected to ij, or I1, if and only if j1, if and only if I is connected to j, and everything else which goes between two different levels you connect. So I0 is always connected to J0, and I1 is always connected to J1. And the fact that was, actually the fact that did have some interest today is, then I said that you, in fact, you had two different ways of writing. The algebraic fact was that this thing could be written in two different ways as a semi-direct product with z2 to the n, and it was also equal to what I call WO gamma, semi-direct product z2 to the n. I don't know why I'm doing all this right now, but the point was that in some sense the usual cubical complex for the universal covers of these was the same. And the picture I was like to draw, so you can sum two, this would be the real picture for the universal cover of the two torus, but that's 1 and that's 2, and here's -1. Yeah. So everything sits, originally sits inside so if I look at this, at things inside 0, 2 to the n, inside here, this was the fundamental domain for the torus. So when I identify the sides, this gives me the n torus, and basically, well, I mean, there's different size cubes in here, but this piece is the fundamental chamber for the right-angled Coxeter group generated by this double graph, and this little square there, something inside the little square, ended up being the fundamental chamber for this thing, but maybe not the described for that. But the point of all this was, the only point I wanted to make was that the link of a vertex in the universal cover of the Salvetti complex, which meant basically the link of something here. It wasn't the Phi complex associated to gamma, it was the Phi complex associated to the double of gamma. Okay, that was one point for doing this. So the link is equal to the some Phi complex for the double of gamma. In other words, just in this picture, I forget where the original thing that has the link of something in one of these cubes might be a simplex, but here I get four copies of the simplex. When I'm looking at this wasn't really important. Just doing this because I made a mistake. So the first thing I wanted to talk about today, that's where the clock is up there. I'm looking down there. Is I probably should have done this at the beginning, but I want to talk about what Koji said he was hoping I would talk about, like cat zero spaces, which is related to but different from hyperbolic spaces. And one of the main facts I've been saying is that these cubical complexes were cat zero cubical complexes. But let me just see if I can run through the standard definition for this. So I'm just going to use X to stand for some geodesic metric space. You heard that last time. That meant that between any 2 points, you could find a geodesic, a path, so that the length of that path was equal to the distance between those 2 points. And once we have that, we can talk about the idea of a triangle. And this really just means 3 points connected by 3 geodesics. And the idea of cat zero is that say it somewhat the same way we do for hyperbolic. It's that triangles are supposed to be thinner than they are in than Euclidean triangles. We're supposed to. But the actual definition is this: you take your space X. So now I'm going to describe what's called the cat zero inequality. Take 3 points in your space X. You join those by geodesic segments, so this is all an X. Now those are 3 distances. It's a metric space. They satisfy the triangle inequality, so you can find three edges in Euclidean space with exactly the same lengths. So this is in R2 or E2. Then if I take 2 points on 2 of these edges, actually you can let one be a vertex, but just take 2 random points, say X and Y, on 2 of the edges, and then we can find the corresponding points over here on this Euclidean triangle. So in other words, this point X prime has the same distance along this segment as X did along this segment. And then you can look at the distance between those 2 points in the 2 spaces, and what's called the cat zero inequality is that this distance is less than or equal to the distance in Euclidean space. So this is called the cat zero inequality. This technique of comparing distances in triangles is an old technique in differential geometry. Oh, I call this X prime, yeah. Well, I just had the other way around to change which is the primes. Okay. Oh yeah, so one of the questions people always ask is, what does the CAT stand for? And this is terminology of Gromov, and apparently whenever you ask him he gives different answers, but one answer is Cartan, Alexandrov, and Topologov, who use these comparison triangles, and other times the C stands for comparison instead of Cartan, I think. He's had other people tell him, he's given that answer to different people, I think. Now, so you wanted triangles to be thin for this definition of delta hyperbolic, but actually you really only cared about big triangles being relatively thin. Here we're interested in all size triangles, and so in fact the thing that comes up is we say that X is non-positively curved if the cat zero inequality holds locally. In other words, around every point there's a small open set where all triangles in that open set satisfy the cat zero inequality. Oh yeah, and the other question, I think Milner, this is one of the few questions Milner ever asked me in my life. He said, what does cat zero stand for? And I said what I said. And he says, and zero? And the zero stands for the fact that Euclidean space has zero curvature. You could also do this for the triangles in the other constant curvature spaces, namely a sphere or the hyperbolic plane. So people have also talked about cat 1 or cat minus 1. So here are the standard consequences of sort of global cat zero. Well, one is that there's if you pick one, there's a unique geodesic between any 2 points. So in fact, if you had 2 points and you had 2 geodesics like this, then you could subdivide one of those geodesics and get a triangle, and then the comparison triangle for this would just be a degenerate Euclidean triangle. It just looked like the line repeated twice. So in fact, the cat zero says the distance from the point any point here to the corresponding point over there has to be 0. So it's unique geodesics, and more generally you can show, you can use this, you can then say pick a base point, and you can use this to show that the whole space is contractible. It takes a little bit more than just unique geodesics, but cat zero implies contractible. And the reason is, you pick a base point, you take any other point y, you connect it by a unique geodesic, and then you can contract along that geodesic. You can use geodesic contraction just to shrink it along that. You need to show that that's a continuous homotopy. That takes a little bit more work. Cat zero, the distance function is. And now the first theorem here, which people always say is, which Gromov calls the Cartan-Hadamard theorem. Is that if X is non-positively curved, and maybe I should say, I probably have to put complete in here. But if it's complete, non-positively curved, and simply connected. So non-positively curved means it's locally cat 0, that implies it's globally cat 0. That any size triangle satisfies cat 0, and in particular it's contractible. And so the corollary of this is that if, say, X is, say, a compact, say, a finite aspherical, say, a compact, so which would be enough to be complete, and aspherical, meaning it's fundamentally, it doesn't have any higher homotopy groups, then that implies that its universal cover is cat 0. So that's the main facts about cat 0. Now we wanted to talk about when cubical complexes were cat 0. So in fact there's a very simple condition for this, which we've seen before. So in general, if X, suppose X, this came up last time when we were talking about, when Koji, I guess, was talking about the RIPS complex, but suppose X is a cell complex consisting of Euclidean polytopes, where the cells are with Euclidean polytopes as cells. For example, they could all be cubes of the same edge length. Then you can define the distance between 2 points. So in other words, in some Euclidean cell, the distance is just Euclidean distance, and then we can promote that to a distance on the Euclidean cell complex. We can define the distance between 2 points to be the inf of the length of gamma, where gamma is, if you like, a piecewise Euclidean path. And if that inf is realized, then that path would be a geodesic. So you can make one of these Euclidean cell complexes into a metric space, and in particular, if you have a cubical complex, if you're given a cubical complex, say if X is a cubical complex, where you put a metric where, say, all cells have, all cubes have, say, edge length 1 or some edge length. Then that has this natural metric. And X has a piecewise Euclidean metric, PE for piecewise Euclidean metric. So you can do it for cubes, you could do it for in these other contexts if you say have simplices of a certain shape. And the question is, when is one of these things non-positively curved? Or when is its universal curve cat 0?
Right?
Yeah.
So, hypothesis of the corollary, compact aspherical and
what, connected? No, what's wrong with that?
I mean, just compact aspherical topological space.
Oh, and non-positively curved. Right, sorry. Okay. Compact and incomplete. Yeah, sorry. So I don't know if I should just, I think I'll just state this, because then I'm going to get on to something else. Maybe I'll state it. So here's, I've called this Gromov. So it turns out that there's sort of local conditions to tell when X is locally cat 0. For example, if it's a two-dimensional structure on a two-dimensional surface, the condition is that the sum of the angles around the vertex is bigger than or equal to 2 pi. But the only time this condition really works easily is what's in Gromov's original paper called his Gromov's lemma. Yeah, I think I'll just say it like this. And this is a condition that works for cubical complexes. So if I have a cubical complex, well, the good thing about that is the length of a vertex in a cubical complex is a simplex, and in fact it's a very nice simplex. So the length of a vertex in a square is a arc. It looks like that. You can think of that as an arc of a circle of length pi over 2, if you normalize things right. And then, say, in a cube, you can think of the length of a solid cube. You can think of the length of a simplex. The length of a vertex in the cube is being this spherical triangle where all the angles are pi over 2. It's a spherical triangle with vertex at the North Pole, 2 vertices on the equator, and all the edge lengths are pi over 2. It's a piece of an octant like that. So in fact, in a cubical complex, you always get the link is always a simplicial complex, and in fact it always has this nice local structure of a piecewise spherical thing. And so I'm leaving, okay, here's what Gromov's lemma says. It says a cubical complex X is non-positively curved if and only if some condition is satisfied for the length of each vertex, if and only if the length of any vertex is a flat complex. Actually, the way he stated this, another way to state this is actually you might say that a piecewise spherical, PS for piecewise spherical simplicial complex is with simplices like I have over there, so I'll say with all right simplices, meaning all the angles are right angles. And then the right thing to say would be cat 1, meaning that it satisfies these comparison things with respect to the 2-sphere, if and only if it is a flat complex. So I'll draw some pictures to illustrate this, although the proof, this is actually proved in Gromov's first paper on hyperbolic groups. So the corollary of this, it says that X tilde, the universal cover of a cubical complex is cat 0, if and only if the length of each vertex, is a flat complex. For all V. Maybe I should keep going with categories, with corollaries like this. So in particular, once I have this lemma, and this gives me a proof of these complexes, which I said were for the work contractible, it gives me a proof that they're contractible. So for example, the two complexes I've been talking about, where I said you take the cubical complex, which gives you the right-angled Coxeter group, so this is what W gamma acts on. Or you can take the Salvetti complex, which is this subgroup of, which was in fact the Z gamma for a circle, comma, 1 point. So it's contained in the torus. This was the space where the Artin group acted on it. And the corollary of this is that both of the universal cover of both of these things is contractible, which is one thing I needed. And similarly, that this one is contractible. So in fact, I basically said, well, we proved this before by some simple inductive argument. Well, first of all, the proof of one is that this construction was set up so that the link of any vertex in one, the link of any vertex was in fact equal to the phi complex for gamma. So the phi complex of a graph is a phi complex. Actually, Gromov didn't call this phi complex. I once heard he called this the no delta condition or no triangle condition. And when I first once heard Besvina give a talk on what I'm going to talk on next, and Gromov was in the audience, and Besvina said, "This is Gromov's lemma," and Gromov said, "What's a phi complex?" Besvina had heard that word from me, and he just couldn't believe it. He said, "Well, that's your condition." Gromov says, "I don't know what you're talking about." It's interesting. I didn't say anything. Although it was my fault. Okay, and to prove this second thing, you need to know that in the Salvetti complex, the link is a phi complex, but in fact, you can either check this from the definition or the point is the proof of 2 is that in X, or X tilde, the link of any vertex, well, it's not necessarily, it's not the phi complex of gamma, it's the phi complex of this double version of gamma, but it's still a phi complex. It's different. So we'll say we've seen both of those. So now, what's the picture I was going to draw to explain why Gromov's theorem makes intuitive sense? So if you think about something like the surface of a cube, of just one cube, so that's topologically that's a 2-sphere. So I take the surface of a cube, I claim that isn't non-positively curved. And if I look at a vertex here, what I see is I basically see I see something that's topologically a circle made out of 3 lengths, and they each have length pi over 2. And the claim is that that doesn't satisfy. So this is not non-positively curved. But in fact, why does it violate the cat zero inequality? So the picture I like to draw with this is, you can think of locally, you can think of this surface of the cube. I mean, you can straighten it out near an edge, but it looks like this. You have three squares put together, and then you identify, say, this side with this side to get some sort of cone, where the cone angle is 3 pi over 2. Now, if you want to take, say, a point here, x, and a point here, y, which is also over there, the geodesic is just a straight line like that. It's a straight line like that. And when you identify those edges, you get a little diagon that goes around the cone point. And so that, you can have that no matter how small this is, so it violates CAD 0 locally. Because you can make that into a triangle, and it doesn't satisfy the comparison condition. On the other hand, if I had something where I had maybe 5 squares, each of these are squares, 5 squares getting together, then that is locally CAD 0. And then you don't have this phenomenon. Then, in fact, the geodesic from a point here to a point here actually looks like you've run into the cone point and then run out. Okay. So at one point, when I was optimistic, I thought I could have time to prove ground level center, but I think that's it for CAD 0. Now the last part I want to talk about is this interesting application that Betsvina and Brady had to right-angled Artin groups and their CAD 0 properties. This was around, I don't know, 95 or 96. So it's old stuff too. But it solves some important theorem in geometric group theory. It was an old conjecture. So I want to explain this conjecture first of all. So there are these things called finiteness properties of groups. I'm usually thinking of infinite, usually torsion-free groups. So the first property, you can say a group is, say, type Fm. This just means that you can find a model for BG, which is some CW complex whose M skeleton is finite dimensional, whose M skeleton is a finite complex. So you only have to, up to dimension M, to build this, you only have to use finite number of cells. And type F just means there is the things we're usually interested in. There's a model for BG, which is a finite CW complex. And then there's algebraic versions of this, which we usually call, say, FPM or FP. So these are algebraic versions. FPM means that you can find I usually think of, it doesn't do much harm to think of P means projective, but you can usually think of it as being free. It means you have a partial resolution by finitely generated projective modules like this. So these are finitely generated projective ZG modules. For example, if you had something of type Fm, you could look at the chain complex, the cell complex, the chain complex for its M skeleton, it would look like this. And these would even be free. Or Fp is supposed to be the analog of this. It means finitely generated there exists a finite projective resolution. So here was what here was the standard thing people said. I can remember this being said as a problem, even before they did it. So the first thing you said is that if you have type F1, which is the same, turns out to be the same as type FP1, and that's the same as saying the group is finitely generated. It says that you can find a model for BG with finite one skeleton. And then you say, what about F2? So F2 is the same as saying the group has a finite number of 2 cells that is finitely presented. But the question is, FP2 just says this homologically. It doesn't say that you can actually, so the question is more or less, is this the same as FP2? And versions of that. And in fact, that turned out to be known to be the only problem with these two things being different. At least, especially if I said free module instead of projective module. So for example, I think Wall proved that if, say, M is bigger than 2, then FPM plus finitely presented implies FM. You might worry, I think there's a trick, if I remember right, I think there's a trick for changing, in this case, for at least the low part, for changing projective modules into free modules. If not, Sayre uses terminology. If you write FL, L stands for free. It's French as libre. This means free ZG modules instead of projective. So in general, he also said that in general, if you notice type FL, which is morally the same as FP, plus finitely generated, that implies type F. So finitely presented. So the only difference, the main difference is right here, right, where it was unknown if there were any examples. Maybe I should just go ahead and state their theorem. I wasn't going to do it this order. You'll state their theorem and then say some examples of this. So what Nasreen and Brady did is it was a geometric argument, but it had something to do with this right angle argument. I'll explain how they thought of this later, but so they said you take this right angle argument and you take the epimorphism to the infinite cyclic group, which sends each generator, this has a generator for each vertex, so this sends each generator, say GI, goes to the generator of Z, goes to 1, okay? And then you look at the kernel of that, and let's call that either H gamma, or to fit with their terminology, I might call it HL, or HL of gamma. All those things being the same thing. So, anyway, the L comes into it, not the gamma. And now what's their theorem? The theorem says this, okay, so the theorem says that HL is type FM. Let's see, I have to get this right. If and only if so F2 should be, yeah. L is homologically, I think I want to say, M plus 1 connected. When I get to the examples, we'll see if that's right. Homologically M plus 1 connected means that the homology of L, reduced homology of this is 0 for star less than M plus 1. And second part of this is that HL is in fact is FP if and only if L is acyclic. And the second part is that HL, let's say, is type F2. Well, FP2, this should have been FP. FP2 is the same as saying that its first homology was 0, of L is 0. F2 turns out to be the same as saying that L is simply connected. So I have to have simply connected to get finitely presented. This is the same as finitely presented, and HL is type F. If and only if L is acyclic, has no homology, and is simply connected. So that means if and only if L is contractible. So what's let me just say, maybe let's just, okay, so there were some examples of things like this were known before, were actually famous example. Well, the corollary of this is, the answer to the problem was that if I take L to be a complex, which has no homology, but has some fundamental group, then it will be a group which is type F, but not type FP. So all I have to do is take a group, take a simplicial complex, which has no homology, but its fundamental group is not trivial. We can do that since you can have groups whose abelianization is trivial. So let me, so here's some old examples which fit into this definition. So, so the first, maybe if you take just the free group on 2 letters, this means the free group. So this is the one that corresponds to, there's L, or L of gamma, it's just 2 points. And then we get that H of L is in fact not finitely generated. So you can convince yourself of this, just take the homomorphism to Z and the universal cover looks like an infinite string of circles like that. So its fundamental group is not finitely generated. If you take the next one up, F2 cross F2, then you get something like this. You get the join of 2 points with itself, because you put in edges when things are supposed to commute. So this is in fact a circle, and the answer is that H of L is finitely generated but not finitely presented. And then the third example is actually I think where they started, these two were probably known, but this is an example due to Stallings, who said by more or less the same argument that if you take the product of three F2s, so then you get the drawing of 2 points with itself 3 times, you get the boundary of an octahedron. That's supposed to be an octahedron. In any case, it's a triangulation of the two-sphere, and this turns out to be F2, but not F3, or not FP3. Not F3. That was like the first example of a group that had that property. And in fact, Pesvina and Brady are saying that this would have worked for any flag triangulation of a sphere. And then Beery continued the same thing. Beery noticed that the same thing went for product of m copies of m+1 copies of F2, that you got something that was whatever it is, Fm, but not Fm+1, or Fm, m+2 copies. Okay. So as I say, the interesting case here is really where L is a two-dimensional, or say a simplicial complex, which is not simply connected and doesn't have any homology. So there's examples like that in dimension 2. So the title of their paper in Inventiones has the word Morse theory in it, combinatorial Morse theory. So I'll try to say something about the picture here, and then I'll say how they prove this. So the picture is you look at the universal cover of this x2 tilde gamma. I don't know how to draw that. Maybe I'll just draw that like it was R2 divided by squares. And then we have this map phi from right-angled arc group to Z, which is basically the sum of the exponents in a word for this. So here's 0, 1, 2. And you have this map from the vertices, which correspond to the elements of A of gamma, to these to the integers, and in fact, on each cube you can extend that to a linear map, and so you can extend this to a piecewise linear map. So say the things that go to 0, all those are, I didn't draw this very well. There's 0. So if you draw the line through one level of vertices, those are all the vertices that go to 1. So these horizontal lines all go to the same thing, and we can extend this to a map F from x tilde, maybe I'll just use x tilde from now on, from x tilde to the real numbers. And their idea was, and if you take any one of these level sets, if you take a level set, which we'll say, look at F inverse of T, then this is acted on by this group H sub L. So H sub L acts on these horizontal level sets. The whole space is contractible, but these level sets don't have to be contractible. So what Pesvina and Brady said is, let's analyze how these level sets change as you cross a vertex. It's easy to see they don't change if you don't cross a vertex, but they change as you cross a vertex. And at a vertex, you have this picture. Say below, here's H of F inverse of T minus epsilon, and here's F inverse of T plus epsilon. And the way it's changed when it goes across this vertex is basically the level set has changed by, well here it looks like it's whatever is in here. This just looks like an interval, but it's changed by coning off that interval. If there was no interval in there, the level set would have changed by attaching the cone onto this part, and this part is what they call the descending link. So they look at this complex. They look at this complex I drew before, like this. They have this function going on it. The whole link, the link looks like O of L, but you have the directions which go down and the directions which go up. And they call the directions which go down the descending link, and the directions which go up the ascending link. So the descending link, the directions which go down in this case, is just equal to a copy of the original L of gamma, or L, okay? So their general observation, their general idea, which they explain in there, is that each time a level set crosses a vertex, you change the homotopy type by attaching the cone over a descending link. By adding the cone on link. This means cone. So, for example, things can start becoming connected. Okay, so that's their idea. Let me just say write down 3 last things, how they did this in practice, and then I'll go back to sort of the two general lemmas that they need. So the first one, which is, you can either say it as a statement about, it's a variation of what's called, it's a theorem in lemma homological algebra, but it just says something like this. If I have a projective resolution that looks like this, where these are finitely generated projectives, and say the kernel I'll call Zm plus 1. Zm plus 1 stands for the cycles in the m plus first homology of something, okay? So this is just, but it's just defined as the kernel. Then the result is that then, this is, maybe I'm supposing we're type FM, which means we have a projective resolution that looks like that. Then the conclusion is then it's type FM plus 1, FPM plus 1, if and only if Zm plus 1 is finitely generated as R. We're talking about this group, some group H. H is a group, as a ZH module. So there might be different ways to construct this first part of the sequence, but it says whether or not the kernel is finitely generated or not doesn't depend on the first part of the resolution. That's just some simple homological algebra. And then there's a version of that for fundamental group. It says something like this. Suppose that the geometric version of this refinitely presented says that suppose that H acts x on a space y, which is connected, then h is finitely presented if and only if you can attach finitely many orbits of H cells to make it simply connected. So that's another definition of finitely presented, if you like. Okay, so in the last 3 minutes, let me just say what so I haven't really said how they use CAD0. They use something about this geodesic contraction I talked about. Actually, there's some technicalities. They look at subcomplexes of the space X, which are just a sort of union of these sheets. But anyway, let's just ignore that. We only have 2 minutes left. So let's suppose we let J stand for any closed interval, a point or closed interval. And I'll let X tilde sub J be the sublevel set, F inverse of, say, of J. So here's their first theorem. So actually the second theorem includes the first, but this one is easier to prove, but I'm not going to prove it. But it says if you take the homology of X comma Xj, that in fact this is the same as the homology of the cone on the descending link of a vertex. Oh, should put a big sum here. It's a direct sum of copies of the cone on the descending link, which is L, a direct sum over the vertices which don't lie in this sublevel set. And equivalently, it says that the cohomology of, then you have an exact sequence of this pair. X is contractible, so it doesn't have any homology. So this gives you say, J minus first homology, the star minus first homology of Xj, so you reduced, is the same as the direct sum over these vertices that are not in Xj of the reduced homology of the link of L. And this is as an RHL module, or ZHL module. What that means is that HL, well this HL acts on this thing. We're thinking of it as acting trivially on these copies of the homology of the link, but it permutes the vertices. It permutes the vertices in the horizontal direction. Okay. So the vertices get changed. So just to say why that implies the first part of their theorem, the homological version is this says, for example, this says suppose L is homologically M connected, whichever it is. What did I say up there? Homologically M plus 1 connected. So that says that L has no homology below dimension M plus 1. In M plus 1, M plus 1 or M plus 2, anyway. In dimension M plus 2, it might have some homology. So then I have that the homology of Xj looks like this direct sum of, say, this I guess is m plus 2. I might be off by the indices at this stage of the thing, of L. But here, this is the vertices which aren't in xj. So if I look at any proper interval, this is going to have an infinite number of levels. It's going to miss an infinite number of integers. So this is going to be infinitely generated. So basically, this plays the role of what I called over there z, or zm plus 1. Maybe I should have been calling it zm plus 2, I guess. So by that generalization of Schnoll's, I don't know how to say it, somebody's lemma, that implies it's fp but not fp m plus 1. And similarly, I can make it type fp. If all these homology groups vanish, then I never get any. I always have that the kernel here is finally generated, so I can always add more cells to kill it. Finally, is homotopy equivalent to a wedge of L's? It's homotopy equivalent to a wedge of copies of L where over all vertices not in xj again. So by more or less the same reasoning, this says the fundamental group of this, if L is not simply connected, the fundamental group of this xj is not 0. And moreover, to kill it, you basically you have to add infinitely many orbits of cells, because an h orbit of cell only kills things on the same horizontal component. So you have to kill infinitely many horizontal lines of these L's, and that takes infinitely many h orbits. So this implies this is what you need to get the second part of the part 2 of their theorem. So at various stages I was going to, there have been other uses of this Morse theory idea, not just to look at functions to R. Another use has been to analyze groups by looking at, say, the distance from a base point and analyzing how the spheres change their topology, and sort of the way I indicated with examples of manifolds not covered by Euclidean space. But this resolved an old problem about the difference between fp and f, and it also introduced this new idea of using sort of a Morse theory on cell complexes to prove things about groups. I'm finished.